One could fit inside a city, the other could swallow our entire solar system whole. One forms when a massive star dies, the other sits at the heart of almost every major galaxy, growing to sizes that defy comprehension. These are black holes. But not all black holes are created equal. The difference between a stellar black hole and a supermassive black hole? It's not just size, it's the difference between a car crash and a galactic apocalypse, between a cosmic corpse and a galactic engine, between something that weighs as much as a few suns and something that weighs billions. And right now, you're orbiting one of these monsters. A supermassive black hole sits at the center of the Milky Way, 4 million times more massive than our sun, and we're all spinning around it at 500,000 miles per hour. So let's break down what makes these cosmic beasts so different, and why understanding them matters for everything we know about the universe. But before we dive into the details, if you're fascinated by black holes and want to see more mind-bending space content like this, go ahead and hit that subscribe button. We're covering everything from stellar explosions to the edge of the universe, and you definitely don't want to miss it. All right, let's get into it. First, the basics. What exactly is a black hole? A black hole is what happens when you pack so much mass into such a small space that gravity goes absolutely insane. The gravitational pull becomes so intense that nothing can escape, not even light. That's why they're black. There's a boundary around every black hole called the event horizon, the point of no return. Cross that line, and you're done. No force in the universe can bring you back. Inside the event horizon, space-time itself gets warped so severely that all roads lead to the center, to a point of infinite density called the singularity. Time stops making sense. Space breaks down. The laws of physics as we know them crumble. But here's where it gets interesting. Black holes come in wildly different sizes, and those size differences create completely different types of cosmic objects with completely different behaviors. Let's start with the smallest type, stellar black holes. Stellar black holes form when massive stars die, and I mean massive, at least 20 times the mass of our sun. These giant stars burn through their nuclear fuel incredibly fast, sometimes in just a few million years. When the fuel runs out, the core collapses in a fraction of a second. For most massive stars, this collapse triggers a supernova, one of the most powerful explosions in the universe. The outer layers get blasted into space at a significant fraction of the speed of light, while the core implodes to form either a neutron star or a black hole. But here's something wild that scientists have discovered. Some stars don't explode at all, they just vanish. The entire star collapses directly into a black hole so quickly that there's no explosion, no supernova, nothing. The star is just there one moment and gone the next. Scientists call this failed supernova or direct collapse. Cygnus X-1, one of the first black holes ever discovered, probably formed this way. The star that became the black hole was originally about 40 times the mass of the sun. It lost most of that mass through powerful stellar winds before quietly collapsing into a black hole of about 14 solar masses. No big explosion. The star just disappeared. These stellar black holes typically range from about 3 times the mass of the sun up to maybe 100 solar masses. That might sound huge, but in cosmic terms, they're actually tiny. The event horizon of a 10 solar mass black hole is only about 60 kilometers across. You could fit it inside a mid-sized city. Despite their relatively small size, stellar black holes are incredibly dense. If you could somehow scoop up a teaspoon of material from near a black hole's event horizon, it would weigh about 1 billion tons. That's roughly the weight of Mount Everest, compressed into a volume you could hold in your hand. Stellar black holes are hard to find when they're alone, drifting through space. They don't emit light, and space is really, really big. But when they're part of a binary system, orbiting a normal star, they become visible. The black hole's gravity pulls gas from its companion star. This gas doesn't fall straight in. It forms a swirling disk around the black hole called an accretion disk. Friction in the disk heats the gas to millions of degrees, hot enough to emit X-rays. That's how we detect most stellar black holes, by the X-rays coming from their accretion disks. As of now, scientists have confirmed dozens of stellar black holes in our galaxy through X-ray observations, and we've detected even more through gravitational waves. When two black holes merge, they send ripples through space-time that we can now detect here on Earth with observatories like LIGO. The first gravitational wave detection in 2015 came from two stellar black holes, 29 and 36 solar masses, colliding 1.3 billion light-years away. Now let's jump to the other extreme. Supermassive black holes. These monsters live at the centers of galaxies, and they're in a completely different league. We're talking millions to billions of times the mass of the Sun. Not hundreds. Billions. Our own Milky Way has one. It's called Sagittarius A, and it weighs about 4.3 million solar masses. It sits about 26,000 light-years away from us, at the galactic center. Scientists have been tracking stars near Sagittarius A for decades, watching them whip around at incredible speeds. One star, S2, completes an orbit around the black hole in just 16 years, reaching speeds of nearly 5,000 kilometers per second, almost 2% the speed of light. But Sagittarius A is actually pretty small as supermassive black holes go. The black hole at the center of M87, a giant elliptical galaxy about 55 million light-years away, weighs 5.4 billion solar masses. That's over 1,000 times more massive than ours. And this is the black hole that made headlines in 2019 when the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow. That image is mind-blowing when you think about what you're seeing. The black circle in the middle is the black hole's shadow, the region where light can't escape. The glowing ring around it is superheated gas in the accretion disk, some of it moving toward us, some away, creating that distinctive asymmetric brightness. The entire ring is so massive that a beam of light traveling at 670 million miles per hour would take 2.5 days just to cross it. But M87's black hole isn't even close to the biggest. Meet TON 618. This hyperluminous quasar, located over 10 billion light-years away, contains one of the most massive black holes ever measured. Recent estimates put it at about 40 to 60 billion solar masses. Let me put that in perspective. That's more than the combined mass of every single star in the Milky Way galaxy. It's over 15,000 times more massive than Sagittarius A9. The event horizon of TON 618 has a radius of about 1,300 astronomical units. An astronomical unit is the distance from Earth to the Sun, so the radius alone is 1,300 times that distance. For comparison, Pluto orbits at about 40 astronomical units from the Sun. You could fit over 30 solar systems, edge to edge, across TON 618's event horizon. A beam of light would take weeks to cross from one side to the other. Let that sink in. We're talking about an object so massive, so large, that it makes our entire solar system look like a speck of dust. And there might be even bigger ones out there. Phoenix A is a supermassive black hole candidate with an estimated mass of up to 100 billion solar masses. At that scale, we're pushing the theoretical limits of how big black holes can even get. So how did supermassive black holes grow to such enormous sizes? Honestly, we're not entirely sure. One theory suggests they formed early in the universe's history through direct collapse. In the first few 100 million years after the Big Bang, there were massive clouds of pristine hydrogen gas. Under the right conditions, these clouds could have collapsed directly into massive black holes, skipping the star formation stage entirely. Another theory proposes that they started as stellar black holes and just kept growing. They ate gas, dust, and even other black holes over billions of years. Every time a supermassive black hole swallows something, it gets bigger. And when two galaxies merge, their central black holes eventually merge too, creating an even more massive black hole. But there's a problem with that idea. For a black hole to grow by swallowing matter, there's a limit to how fast it can eat. This is called the Eddington limit. When material falls into a black hole, it heats up and emits radiation. If the black hole tries to eat too fast, that radiation pushes away the incoming material. It's like trying to drink from a fire hose. At some point, the pressure just blows everything away. Given the Eddington limit, it's hard to explain how some supermassive black holes got so big so fast. TON 618 existed when the universe was less than 1 billion years old. That's not much time for a black hole to grow from stellar mass to 60 billion solar masses, even if it's eating as fast as physically possible. Maybe they started bigger than we thought. Maybe the Eddington limit doesn't always apply. Maybe there are mechanisms we don't understand yet. This is one of the big open questions in astrophysics. What we do know is that supermassive black holes have a profound effect on their host galaxies. They're not just passengers sitting in the galactic center. They actively shape how galaxies evolve. When a supermassive black hole feeds, it creates what's called an active galactic nucleus, or AGN. The accretion disk around an actively feeding supermassive black hole is stupendously hot and bright. Some AGNs are so luminous that they outshine their entire host galaxy by a factor of 1,000. These super bright AGNs are called quasars, and they're among the most luminous objects in the entire universe. TON 618 isn't just a supermassive black hole, it's a quasar shining with a light of 140 trillion suns. That's brighter than most entire galaxies. Many supermassive black holes also produce jets, narrow beams of matter and energy that shoot out from the poles at nearly the speed of light. These jets can extend for millions of light years, far beyond the galaxy itself. The jet from M87's black hole, for example, stretches over 5,000 light years into space, visible in radio wavelengths. These jets carry enormous amounts of energy. They plow through intergalactic gas, heating it up and preventing it from cooling down and forming new stars. In this way, supermassive black holes regulate star formation in their host galaxies. They're like cosmic thermostats, controlling how much fuel is available for making new stars. There's even evidence that there's a relationship between the mass of a galaxy's supermassive black hole and the properties of the galaxy itself. Bigger black holes tend to live in bigger galaxies. It's as if the black hole and the galaxy co-evolve, growing together over cosmic time. Stellar black holes don't have this kind of galactic influence. Their effects are local, limited to their immediate surroundings. A stellar black hole might strip gas from a companion star or occasionally eat a passing object, but it's not shaping the evolution of the galaxy. It's just one object among hundreds of billions of stars. The detection methods for these two types of black holes are also different. For stellar black holes, we rely mostly on X-ray observations and gravitational waves. We look for X-ray binaries, systems where a black hole is pulling material from a companion star. The X-rays tell us something is there, and by studying the orbit of the companion star, we can figure out how massive the invisible object is. Gravitational waves have opened up a whole new way to find stellar black holes. LIGO and Virgo have detected dozens of black hole mergers, events where two stellar black holes spiral into each other and collide. These mergers emit no light, but they produce powerful gravitational waves that ripple across the universe. By analyzing these waves, we can determine the masses of the merging black holes and learn about populations of black holes we couldn't detect any other way. For supermassive black holes, we use different techniques. We track the motion of stars or gas near the galactic center. If stars are orbiting very fast around an invisible point, there must be something massive there. That's how we confirmed Sagittarius A star is a black hole. We also use a technique called reverberation mapping for more distant supermassive black holes. Light from the accretion disk illuminates gas clouds farther out. By measuring the time delay between changes in the disk's brightness and changes in the cloud's brightness, we can figure out how far apart they are. Combined with the velocity of the gas, that tells us the black hole's mass. And then there's direct imaging. The Event Horizon Telescope used a network of radio telescopes spread across the entire planet to create an Earth-sized telescope, giving it enough resolution to actually photograph the shadow of M87's black hole. That was a historic achievement, turning something we'd only seen in simulations into a real image. One category of black holes I haven't mentioned yet is intermediate mass black holes, with masses between 100 and 100,000 solar masses. These would bridge the gap between stellar and supermassive black holes, but they're incredibly rare. We've only found a handful of candidates, and their existence is still debated. If they exist, intermediate mass black holes might be the missing link that explains how supermassive black holes form. Maybe stellar black holes first grow into intermediate mass black holes, then those merge and grow into supermassive black holes. But we need more observations to confirm this. So what does all this mean for us? Why should we care about black holes? For one thing, they're testing grounds for our understanding of physics. Black holes are where Einstein's general relativity gets pushed to its limits. Near the event horizon, space-time is so warped that weird things happen. Time slows down. Space curves. If you could somehow hover just outside a black hole's event horizon, time would pass more slowly for you than for someone far away. This isn't science fiction, it's real, and it's been confirmed by observations. Black holes also teach us about the life cycles of stars and galaxies. Every stellar black hole is the remnant of a massive star. By studying these remnants, we learn about how stars live and die, and by studying supermassive black holes, we learn about how galaxies form, grow, and evolve over billions of years. There's even a possibility that supermassive black holes play a role in making the universe habitable. By regulating star formation, they prevent galaxies from burning through their gas too quickly. This creates a more stable environment over longer timescales, potentially giving life more time to emerge and evolve. And let's not forget that we live in a galaxy with a supermassive black hole at its center. Sagittarius A star is relatively quiet right now. It's not actively feeding, not producing powerful jets, not flooding the galaxy with radiation. But it wasn't always this calm, and it might not stay calm forever. If a large gas cloud or even a star wanders too close, Sagittarius A star could flare up, becoming millions of times brighter than it is now. Fortunately, we're far enough away that we're safe. But it's a reminder that our galaxy has a sleeping giant at its heart. To sum it up, stellar black holes are the corpses of massive stars. They're relatively small, ranging from a few to a few dozen solar masses, and they form through supernova explosions or direct collapse. We find them through X-rays and gravitational waves. They're numerous, dangerous if you get close, but limited in their cosmic influence. Supermassive black holes are galactic monsters. They weigh millions to billions of times the mass of the Sun, sit at the centers of galaxies, and actively shape galactic evolution. We find them by tracking nearby stars, measuring light echoes, and even photographing their shadows. They're rare but incredibly powerful, influencing entire galaxies over billions of years. The universe contains both, the tiny and the titanic, the local and the cosmic. And we're only just beginning to understand how they work, where they come from, and what they tell us about the nature of reality itself.